Hello, it's Keith here, and this is lesson 36 of the platform-specific series of my 68000 assembly programming tutorials, and today we're looking at the Amiga. I know it's been a while, Amiga fans. I'm sorry I don't know very much about the Amiga because I never owned one. Anyway, today we're going to be looking at some of the more interesting graphics modes that the system can offer. In the past, we'd only looked at the 16 color mode, and the reason for that is that I'm an 8-bit user and I'm used to only having 4 colors, or 16 is incredible luxury. So the 32 colors the Amiga can offer is absolutely amazing, and we're going to be looking at how to use them today. As well as that, we're also going to be looking at how to use multiple playfields, as I believe the Amiga calls them. This is where we can have multiple layers that move separately, independently of each other for some parallax scrolling and things like that, and we'll be looking at that as a second example. Now, the first one you can see here is the 32 color example. It's our classic Chibico, but you can see a nice range of colors at the top there, a lot of shades of gray. That is a 32 color sprite. Now, both of these require us to use more bit planes than usual. We were using 4-bit planes before to get 16 colors, but we'll need to use 5 to get 32, and we'll use 6 to get the 2 layers. And the reason we have to use 6 is that allocates 3 per layer, so each layer will have a maximum of 8 colors. It should be noted, to my knowledge, it's not possible to have all 6-bit planes allocated to one layer, so you can't have 64 colors, at least on the original Amiga. I'm sure later ones had more colors than that, but as I say, I'm really used to 16 colors and things like that, so we won't be going much beyond this. Anyway, that's what we're going to be looking at today. So let's go over to the source code and let's take a peek at how it all works. Okay, over we go. Now, it's pretty straightforward, really, to be honest, to get the 32 colors working. Now, the first thing you're going to need is you're going to need a 32 color sprite, and my Sprite editor has been upgraded. You can go to the 68000 menu, select Amiga, and you can use the new save raw bitmap options. And we had the original one, which was the 4-bit per pixel, but we now have 5-bit per pixel and 3-bit per pixel for this 32 color and the two layer version of the examples we'll be looking at today. So that's how you can create the data that we will need for today's example. And then beyond that, it's all pretty straightforward, really. Now, of course, we're going to need an extra bit plane, and the way we need to do this is we need to allocate some memory. So we're allocating some memory in our chip RAM here. Before we were allocating 4-bit planes, but now we're allocating 5. Our screen is 320 by 200 pixels, and we need 5-bit planes, so we are multiplying that by 5, and that's defining our screen memory there. We are transferring our sprite 1 byte at a time to the multiple layers. Now, this is the same code as we used before in the simple series. I'm not going to go into a great amount of detail on how it works, but basically we're moving consecutive bytes of our source data to the 5-bit planes. So you can see here we're loading to bit plane 0 there where that A6 is marked, and then bit plane 1, 2, 3 and 4 here. That is the 5-bit planes that define our 32 colors. So that's how we're transferring the data to VRAM. We of course need to define all of our colors here. You can see this, we're transferring these color definitions into the copper list, and we've got 32 color definitions here. And if you need to create this block of data here, again, my Sprite editor can do that for you. You just go to 68000 and you go to Amiga, and this copy list palette to clipboard will save the data you need into the clipboard, and you can use that to get the colors from Sprite editor into your program as you need there. Now, we need to define the 5-bit planes in our graphics setting. We use this BPL-con option here, and that is DFF100 here. That's BPL-con 0. That's what we need to do to define the color depth. And it is these 3 bits here that actually do the work of defining what color depth we're using. So this is a value 5 here, and that's the number of bit planes that are in action there. So that defines the color depth, but we also need to define the memory of the extra bit plane. So we're defining the memory for the 5th bit plane here. We're calculating our screen memory plus the offset here. We're effectively transferring the low word here and then a high word here. So that's defining the extra bit plane, and that will allow the Amiga to see it and use it when we run. So that's really all there is to it. It's very straightforward, to be honest. We just need to allocate some extra memory, apply it, set the screen mode, and then we have an example that can show a sprite like this one here. So that's how we get our 32 colors working. Now, our second example we're going to be looking at is getting 2 planes working, and this is pretty straightforward as well. So here is the example we're using here today. So here's the example. So here you can see we've got two layers. There's one layer where all the colors are gray, and the other layer has the Chibico in the normal colors there. And I've also filled all of the background with this kind of random data here. Well, it's actually consecutive bytes, you can probably tell that, but that's just so that you can see that the background layer is moving and the foreground layer is staying static. Well, the foreground layer is actually moving across 1 pixel at a time, because we've got some simple scrolling in place here just to show the scrolling capabilities. Anyway, let's just close that before my eyes go weird, and we're going to discuss what has had to change to get this working. Well, once again, we're having to set BPL 0 here, and we're having to set these 3 bits here, and this time we're setting it to use 6-bit planes, because we're going to need to use 3 for one layer and 3 for the other layer, and they do refer to them as playfields in the Amiga documentation. Now we also have to set this bit here, which defines that we're using double playfields. This was a 0 before, now it's a 1, and that defines that we're using 2 layers. Now another thing that we might want to look at is BPL 2, and this can specify the priority of the layers. Now before, when we ran this, the color Chibico was behind the grey Chibico, but if we swap these over, if we just change that 1 to a 0 here, and we run this again, and I just delete all that garbage I accidentally typed. Well, now you can see that the grey Chibico is behind the coloured Chibico. So we can, if we need, flip the 2 layers priority here, and that will allow us to change how the 2 layers have priority. And we can also set the sprite priority as well. Now we will also be looking at horizontal scrolling, and this uses BPL 1 here. So this, we're starting off as 0, and we're going to be incrementing that later. And another one you might want to know about is BPL mod 1 and 2 here. We're also setting those to 0, and those are relating to horizontal scrolling. Now of course these are all the definitions at the top here. We've got the actual values of them here, so if you're needing to convert this code for your own assembler, you need to convert those definitions. Of course, we've got our colors defined exactly the same way as before. We've got various colors here. Now one interesting thing is the way that the colors are actually split between the 2 layers. Now if I just go over here, so basically Playfield 1 will use colors 1 to 7, and Playfield 2 will use colors 9 to 15. Color 8 and color 0 are basically transparent and go to the background color. Now the other thing that's worth noting is that the bit planes for Playfield 1 aren't bit plane 0, 1 and 2, and Playfield 2 uses 3, 4 and 5. They're actually split differently. Playfield 1 uses the odd bit planes, and Playfield 2 uses the even bit planes. But of course we can allocate the memory to those bit planes however we want. And so what we're going to do is we're going to basically split them out. If I just go over to my blackboard here. So basically, if you think of the bit planes within the hardware, these are the hardware numbers here. So that's our 6-bit planes, and these are basically 0, 2 and 4, and these are 1, 3 and 5. Now what I'm going to do is I'm going to allocate the memory in a more logical way for us to work with these 2 bit planes. So basically, if this is our RAM, I'm going to put bit planes 0, 2 and 4 here, and 1, 3 and 5 here, and then all I need to do is change my pointer so that if I'm going to write to the first layer, I just point my pointer here and I write my sprites to the next 3 bit planes, or if I'm going to write to the second bit plane, I just put my pointer here and then write to the next 3 bit planes, and I will be writing to a separate layer with the same code. So that's what I'm going to be doing. But as I say, the bit planes as they are organized within the hardware are alternating bit planes, and it's just the organization in memory I'm going to make a bit more consistent. So you're going to see that in the code here. Okay, so we've turned on our graphics here, and then of course what we need to do next is we need to allocate our memory again. So here we're defining 6-bit planes again within our chip RAM. So that's our memory, and then what we need to do is we need to allocate all of the addresses for the copper list of the bitplanes. Now I've got this function called set bitplane pos, and we're going to be running this, and we're going to potentially be using an offset. Now what we can do to effect a vertical or a word level horizontal scroll is we can offset the screen by a number of bytes. For example, if we add 40 bytes, we'll effectively move down by one line. So we can use an offset to set a scroll position. But if we set D2 and D3 to 0, we will set effectively the initial starting position of the screen. So what we're doing is we're loading the address of the copper list, and then we are setting all of the bit planes. But as I say, we're actually going to set bit planes 1, 3 and 5 here, and then we're going to set 2, 4 and 6. Now the numbering's different here. I've numbered these from 1 and I've numbered them on the chart from 0, so I apologize for that. But basically we're setting the odd and the even bit planes in a separate section of the memory, and you can see that here. So bit planes 1, 3 and 5 here are set to 0, 1 and 2, and then 2, 4 and 6 are set to 3, 4 and 5. Now the benefit of doing this is we can basically use the single draw bitmap routine, and this is going to draw to the address in A6 offset by 1 bit plane and then 2 bit planes. But then we can use our draw bitmap routine twice, or the only difference is here's the first time drawing to the first layer. We use get screen pos to calculate the address of the destination, and we then run draw bitmap. But then to do the second one, we again calculate the VRAM address, but then we add the offset of 3 bit planes to move to the second layer there, and that will make this second draw of the bitmap go to layer 2. And that's how we've got the second Chibico on the second layer. Now if I take this out and I run again, well, now both Chibicos are on the same layer. And of course, if I added this line here and I put it here as well, then again, they'd now both be on the grey layer. But we're not going to do that because, as I say, I think it's clear what it's doing. So that's how we are drawing our Chibicos to the screen and how we are getting the screen set up for the 2 layers. Now, one other thing we're doing is we are scrolling the screen. Now, we're doing this in 2 ways. Now, BPLCon1 allows us to set a delay which effectively offsets one of the bit planes by a single pixel. So this will take a value from 0 to 15, and it uses the bottom 4 bits of the word that's written for Playfield 1 and the next 4 bits for Playfield 2, and these are the offsets of the 2. And that's why if we look at this animated GIF here, you can see one layer is moving very fast and the other's moving very slowly. The grey bit plane is using these top bits here, so he's getting updated very infrequently there. So that's how we affect a pixel scroll. But what about vertical scrolling or scrolling for more than a single pixel? Well, what we're effectively doing here is using set bitplane pos, which we use to initialize the copper list, but now we are setting effectively an offset. Here we're offsetting D2 here, and that is effectively moving us up the screen because we're adding 40 to D2 each time, and D2 is being used to offset the first layer here, whereas D3 is being used to offset the second layer here. So we can use those to offset the 2 layers by either a word horizontally or a line vertically, just depending on the amount we add. Now, one other thing I am going to briefly discuss, I haven't done a lot of testing with this, but we can actually change the size of the screen. Of course, we can change the vertical size of the screen and make the screen double the height and just use parts of that to effect a large vertical scroll. But what if we want a very large logical screen and we only see a small area there? If I just go over to my blackboard here again, well, let's suppose we've got a huge logical screen here, and then suppose we want to just see a very small window of that. So if this was 40 wide, then we would want our larger screen to be maybe 80 wide. So the way we do this is we actually set an amount to skip after each line. So we would draw our 40 bytes here, and then we would want to effectively skip 40 bytes here. And that's what we can do. So what we do, if I just go back over here, is we actually use these BPL mod options, and these will define an amount that should be skipped at the end of each line, and we can just very quickly test this. If I just rem these out, and I now set an offset of 28, and if we just go over to my calculator here, and if we just put in a value of 40 here, you will see that is indeed 28 in hexadecimal, so that's why we've got 28 in our code here. And if we run this again, because we've not actually specified a larger screen than the visible screen, what this will actually do is it will effectively skip half of the lines. So it's kind of squashed up our Chibico here, and you can see a ghost Chibico, which is, I think that's effectively the other bit plane being shown again there, because we've not allocated enough memory for the viewable area now. But you can see by setting that BPL mod to skip effectively one line worth of data, we have now halved the height of our Chibico, because, as I say, half the data is now being skipped. And I believe that can be used to create a much larger playfield, as I sort of described before. So there we go. So anyway, that's all we're covering today. As always, you can go and download the source code from my website and have a go with it, and I'm sure you can do a far better job of it than I can. If you've liked what you've seen, please like and subscribe, as always. Also, if you want to support my channel, you can buy my book. It's called Learn Multi-Platform Assembly with Chibi Akamas. It covers Z86, 502, 68000, 8086 and ARM, and it's available from Amazon now, either as a real printed paper thing or as a strange digital thing that doesn't really exist. So please buy one of those if you would like to support me and get yourself some programming documentation. Anyway, I hope you've enjoyed this. Thanks for watching today, and goodbye.